Hi, welcome to another 4AC learning video. In this video, we look at example 4.3c, which is found in your lecture notes, topic 4, AC power. Now, a small industrial plant has a 10 kilowatt heating load and a 20 kVA inductive load due to a bank of AC motors. The heating elements are considered purely resistive, that is a power factor of 1, and the AC motors have a lagging power factor of 0.7. If the supply is 600 volt at 50 Hz, we want to determine the capacitive element required to raise the power factor, the overall power factor, to 0.95. So how can we do this kind of question? It's always good to start the question by drawing out a circuit first. Currently, we are told that in this case there are two sets of power source, so you can draw something like that. Say let's call this S1 and we call this S2, because in actual any electrical system the loads are actually connected in parallel. Okay, where the voltage is 600 volt, apply a voltage supply, and we are told that S1 is a heating load, so it only have P1 goes to 10 kilowatt, and S2 is an inductive load, right? But it has a power factor, so S2 is 20 kVA with a power factor of 0.7, which means that it has some resistive load, it has some inductive load, right? And the frequency is given as 50 Hz. So we want to know what is the capacitive element that we must introduce here to improve the power factor to 0.95. Now before we can improve the power factor to 0.95, we need to evaluate the overall power factor before we add on the capacitors first. So that's what we need to do. So the first step is to write down all the loads there. So S1 is P1 plus JQ1, right? Since P1 since S1 is a total resistive load, I can only write 10 kilowatt, where JQ1 is 0. If I want to write, I can just put 0. Whereas for S2, now S2 we are told that the magnitude is 20 kVA and it has a power factor of 0.7, which means the angle cos theta 2 can be calculated as cosine inverse of 0.7, which is 45.57 degrees. Then I can calculate P2 as S2 cosine theta 2. So that's 20 times 0.7, which gives me 14 kilowatt. The reactive power Q2 is S2 sine theta 2, which is 20 times 0.714. That gives me about 14.28 kilowatt. In other words, S2 can be written as P2 plus JQ2. That's equals to 14 kilowatt plus J 14.28 kilowatt. Oh, sorry, not kilowatt. This must be kVAR. kVAR. So the first thing we need to do is add up the total apparent power, or total power, right? So I have S1 plus S2, which is 14 kilowatt plus 14 kilowatt. Sorry, the first one is 10 kilowatt. Now here is 10 kilowatts. 10 kilowatt plus 14 kilowatt plus J 14.28 kVAR. That's equals to 24 kilowatt plus J 14.28 kVAR. This is the, compare this with P plus JQ. Or we can write it in the polar form, 27.927 at an angle of 30.75 degree VA. So in other words, the overall power factor is cosine 30.75 degree, so which is at 0.859. Right? So now what we want to do is to determine what should be the capacitance here. So to do that, it's useful to draw a power triangle and then see how it must change. So the present power triangle is given as follows. P is 24 kilowatt and the Q at the moment is 14.28 kVAR. That gives me an overall power S1 or ST of 27.927 VA with an angle of 30.75 degrees. So in order to improve the power factor, what we want to do is improve the power factor to 0.95. Now this corresponds to an angle of, let's call this the new angle theta 2, cosine inverse of 0.95. That gives me a new angle of 18.19 degrees. In other words, in order for me to improve the power factor, I need to find a way to reduce and form the new ST so that this angle is 18.19 degrees with a new Q with a new Q1 here or Q2 here, right? So that means I need to introduce a capacitance such that I have a new QC that will cancel out some of the inductive reactance there. Now to start with, for the new factor, P remains the same, so 24 kilowatt unchanged. Now if I look at this little triangle here, I can then find my Q2. That means the new Q2. Q2 divided by P is tangent of the new angle 18.19 degrees. Therefore my Q2 is equals to P tangent of 18.19 degrees. That's equals to 24 kilowatt. 24 kilowatt times tangent 18, that will be 7.888 kVAR. Right, that means I want to achieve this. So the QC I need to introduce must be balanced off by that, right? Because if I look at this triangle, this is the original Q, which is the same as QC plus Q2. I know Q2 from here, since I calculated here. My QC must be equals to Q minus Q2. So the original Q is 14.28 minus 7.888. That means my QC must be 6.392 kVAR. Now we also know that QC can be calculated using QC equals to the voltage that we apply, V square, over the capacitive reactance of the new capacitor bank I want to use. So which means that XC must be V square over QC. That's equals to 600 square over 6.392 kVAR. That gives me an XC of 56.32 ohms. And we know that XC is actually calculated from omega C, where omega is 2 pi frequency or 50 Hz. Therefore, rearranging this will be C equals to 1 upon omega XC. That's equals to 1 upon 2 pi 50 and 56.32. That will give me 56.52 microfarad. 52 upon 56. So that means this is the capacitance of the capacitor I need to put in parallel with the main circuit here to improve the power factor to 0.95. Okay, so I hope you learned something about how to answer this type of question. Bye for now. See you.